So next what we're going to do, I'll call this a proposition. What we're going to do is we're going to fix some integer m such that m is greater than or equal to 2. We use m, by the way, because the value m stands for modulus, hence mod m. So modulus is the word that gets thrown around. But we're going to fix an integer m that's at least 2. Say, pick whatever your favorite integer that's at least 2 is, say 4 or 10 or whatever. And what I want to do is I want to consider the following relation. So I'm going to call this R. Some people like to put a subscript m just to emphasize that this changes based on what the value of m is. I guess I'm just going to call it R. But R is going to be defined as a relation on pairs of integers. And the two integers are going to be related if they're congruent mod m. Okay, so A is going to be related to B if and only if A is congruent to B mod m. And what I want to show is that R is an equivalence relation. Okay, so R is an equivalence relation. So first we need to prove that R is reflexive. Okay, so R is reflexive as A is congruent to A mod m for all integers A. I better write for all because this is supposed to be a nice proof. So for all integers A, since m divides A minus A or m divides 0, right? We know that every integer divides 0, in particular m divides 0. And if it divides 0, it divides A minus A, that means that A is related to A for all A. So R is reflexive. R is symmetric because if A is congruent to B mod m, then by the proposition that we just said before, one of the equivalent ways to thinking about this relationship is that there exists an integer k where A is equal to B plus mk. And if that's the case, then B is equal to A plus m times minus k. So B is congruent to A mod m. Okay, so if A is congruent to B mod m, then B is congruent to A, so it's symmetric. And finally is transitivity. R is transitive because if A is congruent to B mod m and B is congruent to C mod m, then there exists integers k and l. So there exist integers k and l where A is equal to B plus mk and C is equal to, B is equal to C plus ml. And therefore, A is equal to B, which is C plus ml plus mk. So A is equal to C plus some multiple of m. Okay, so therefore, A is congruent to C mod m. Okay, so it's reflexive, it's symmetric, it's transitive. In particular, it's an equivalence relation. I want to just write this a little better. So mod m. So R is an equivalence relation. Its equivalence classes, its quotient set, will be familiar to us. So R is an equivalence relation with quotient set. So with quotient set. So remember the way that we denote this is we have R mod Z, and the quotient set is going to be the equivalence classes of 0, 1, 2, all the way up to m minus 1. So I think at this point it would probably be helpful to do this for a specific value of m. So let's look at m equals 4. Then we're going to say that two integers, so the relation that we're going to look at is the pair of integers a and b, where a is related to b if a is congruent to b mod m. The fact that I even call this congruence should tell you that this is an equivalence relation, right? There's some kind of formal equivalence between the two sides. So I might mix up the terms equivalence and congruence because now that we know that this is an equivalence relation, I can say A is equivalent to B. The way that we defined it, I would say that A is congruent to B mod M. So I may use either term. So A and B are going to be related if they're congruent mod 4. Okay. Now let's think about this. Let's think about what are some terms that are going to be related. So in fact, let's kind of classify what's the equivalence class of 1. Well, this is going to be the set of all the integers y such that y is related to 1 mod 4. And if we think about this in terms of the remainder property, so we know that y is congruent to 1 mod 4 if y and 1 have the same remainder when we divide by 4. And so it turns out, what are all the integers that are going to have a remainder of 1 when we divide by 4? Well, that'll include 1, 5, 9, 13, just in going up by multiples of 4, -3, -7, -11. Okay, and so it turns out that all of the integers, you can also write this as the set of integers, let's say 4 times x plus 1, where x is an integer. So all of the integers of that form that are going to be multiples of 4 plus 1 will be this equivalence set. And so that's why you can think of the quotient set as the set of all the remainders, right? In our case, the remainders that we're going to get are from 0 to m minus 1 because we're dividing by m. And so if we have m equals 4, then our quotient set for this relation mod the integers is going to be 0, 1, 2, 3. And I want you to remember two things about equivalence classes. Let me write them down first. So the equivalence class of 0 is going to be all the integers that have a remainder of 0 when divided by 4. These are precisely the multiples of 4. So 0, 4, 8, 12, -4, -8, and so on. The equivalence class of 1 we just found before. So that's -11, -7, -3, 1, 5, 9. The equivalence class of 2 is going to be all the integers that have a multiple, that have a remainder of 2 when divided by 4. So it's going to be things like 2, 6, 10, 14, -2, -6, -10. Okay, again, goes infinitely far in both directions. And then finally, one more. If we were to have multiples of 4 plus 3, we would get 3, 7, 11, 15, and so on. And then in the other direction, -1, -5, -9. Okay, now remember what the two properties of an equivalence relation are, or rather of the equivalence classes. They're disjoint. That means that there's no integer that's in more than one equivalence class. And that should make pretty good sense, because if you have an integer that has a remainder of, say, 1, then it's in this set. It can't also have a remainder of 2, right? That doesn't make any sense, because we know that the remainder is unique by the division algorithm. So it's actually important that we prove the division algorithm. So the uniqueness of the remainder tells us that these really are disjoint equivalence classes. Finally, if you take the union of all these equivalence classes, you get every integer. Every integer is in here somewhere. So if I were to think about 100, that would be in one of these integers, in one of these equivalence classes, right? So every integer is in one of these sets exactly once, okay? So this partitions the integers. So this, I think, is actually the most important example of an equivalence class, an equivalence relation, an equivalence set, quotient set, rather. And this is actually something that we did, I kind of hit it at the time. But if you think about back to I forget if this was on a homework or on an exam or maybe both, but if you think about the example where you had the relation where two integers were related, um, if and only if x and y have the same parity. This was definitely on a homework. I don't remember if this was on, I think the exam was two integers are related if they differ by a multiple of 3. That was basically this exercise where m is 3. And if you think about the relation on the homework where two integers are related if they have the same parity, having the same parity basically means that you're congruent mod 2. So that's the same as saying that x is congruent to y mod 2. Because if you think about what are the quotient sets here, you're going to have 0 or 1. And 0 represents the evens. So here, r mod z is going to have two quotient sets, 0 and 1. Here, this is going to be the set of all the even integers. And the equivalence class of 1 will be all the odd integers. So when you divide an odd number by 2, you have a remainder of 1. When you divide an even number by 2, you have a remainder of 0. That's really all that's going on there. So those were kind of examples of this modular arithmetic relation that I kind of snuck under the radar there in different language. Okay, so this is, in a certain way, this is an idea that we've seen before. No matter what, this is an idea that we will talk about lots more going forward.